Hi there. I was just working on the video for my thesis. The topic is applying quantum computation to gravitational wave research. Let me show you what I've been doing.
When two massive objects orbit each other, they create ripples in space-time, which are called gravitational waves. These waves travel through the universe at the speed of light and interact very weakly with matter, but are detectable with special detectors. On Earth, we have a few such detectors, of which LIGO in the US and Virgo in Italy are the most important. They have two perpendicular arms with mirrors at the end, as well as a semi-transparent mirror at the intersection. A detector is placed facing one of the arm mirrors and a laser the other. When the light touches the semi-transparent mirror, the beam is split in two and travels back and forth through the arms before getting reflected into the detector. The detector is connected to a computer, and when the gravitational waves pass through, a signal is outputted. This signal represents the event as well as the collision, called the chirp. The gravitational waves make the arms oscillate, which causes the signal. These types of detectors are called laser interferometers and are the reason why LIGO is called as it is. Because the arms oscillate, the two beams are going to travel different distances. As such, when they enter the sensor, they interfere with each other, causing the signal. Unfortunately, this signal is very noisy, but if we know the signal shape, we can extract information on the event using a technique called matched filtering. This signal shape is also known as a template. If we combine the signal and the template, we calculate the signal-to-noise ratio, or SNR. This is a measure of how well the template matches the signal. The plot below shows that when the template and the signal overlap, the SNR is maximum. A template matches well when its SNR is above a certain threshold, rho thresh. To find the exact source of the gravitational wave, we need to simulate many events with different parameters and make a template bank. We then apply matched filtering to each one of them and create an array of SNRs. The ones that are above the threshold are solutions. From this, we know the approximate parameters of the event that caused those gravitational waves. Currently, we observe approximately one gravitational wave per week. We can increase this by building new and more sensitive detectors that would see lower frequencies and longer signal. A good example of this would be the Einstein telescope, which would incorporate 3 interferometers into a single building. But these would also generate enormous amounts of data, which we wouldn't be able to handle currently. This problem can possibly be solved by quantum computing. And this brings us to the subject of my thesis, investigating the applicability of quantum computing for gravitational wave research. More specifically, applying Grover's algorithm to matched filtering. And so, what is quantum computing? Well, classical computers can have only bits of ones and zeros. These can be structured and then sent through an algorithm that will be able to output only one solution at a time. Qubits, however, can be put in a superposition of 1 and 0. This is an example of a qubit in superposition, and when put through an algorithm, there can be multiple solutions with different probabilities of being measured. The p's represent the probabilities and the letters are the solutions. When looking at the output of a quantum computer, we see only one solution. But with multiple measurements, we are able to do a histogram showing the probabilities of getting the solutions. The higher the peak, the more probable a solution is. Thanks to these properties of quantum mechanics, some quantum algorithms are much faster than their classical counterparts. And one of these is Grover's algorithm, which we have decided to implement for this thesis. In effect, it is a search algorithm over an unstructured database. In our case, this database is the SNR array, which is then encoded into quantum states. These states have been initialized into an equal superposition, meaning that the probability of measuring each is the same. They are then sent into the Grover's algorithm, which is composed of two parts, the oracle and the diffuser. The threshold is encoded into the oracle, which will then find and mark the solutions. The diffusion, on the other hand, takes probabilities from non-solutions and gives it to the solutions. The output state will then just be a combination of those probabilities, and the measurement will have a high likelihood of being one of the solutions. A histogram gives a good visualization of how the diffusion works. The reason we want to use Grover's algorithm is because it has a quadratic performance increase compared to its classical counterpart. At present, quantum algorithms are implemented as circuits, and as there are a limited number of real quantum devices, we need to make simulations, in this case using Qiskit. We successfully managed to implement the previously mentioned algorithm into a circuit. This is how it looks. It is fully functional and has been tested in many different ways. This means with small, big SNR arrays and also real-world data. And because it is a custom circuit, it is fully configurable. So why are these results important? Well, they were only a first step in a much larger picture, and this gives hope for future research. Important tools have also been built, which will facilitate these studies. Gravitational wave research is not the only field where quantum computing is applicable, as there are similar problems in particle physics, biology, chemistry, climate modeling, and many others. So this project hopefully has helped in the lateral diffusion of knowledge. It is also true that any study in quantum computing is possibly a step towards a computational revolution. It is, however, important to remember that any new technology should be treated carefully, as there's always possibility of misuse and abuse. A great example of this in quantum computing is Shor's algorithm. It can result in an almost exponential speed-up of prime factorization, which can be used to break public key cryptography, like RSA. This means that your personal information, internet privacy, military secrets, and many other things will just be opened for a hacker or a state actor to come and grab. This means that when quantum computers will become usable, we will need to find new cryptographic methods to implement.
Phew. Well, that was a superficial overview of my thesis. For any more information, you can read the paper, of course. All of the material in this video was copyright free. And yeah, thanks for watching. See you soon.